Hello everyone, my name is Vincent Noël and I'm a researcher at Institut Curie in Paris. And today in this session I'm going to introduce you to the notion of intracellular models for PhysiCell. So first I'm going to present you what I mean by modeling intracellular signaling in PhysiCell. Then I'm going to present you PhysiBoSS, which was one of the first implementation of intracellular signaling inside PhysiCell using MABOSS. Then I'm going to present you PhysiBoSS 2, which is the new version of PhysiBoSS, which is now integrated into recent PhysiCell. And finally, I'm going to present you the intracellular interface, which is made to glue together PhysiCell and intracellular models. So first of all, PhysiCell has a very simple view of intracellular signaling, and this is what where everything starts in this effort. So for example, PhysiCell has a notion of cell cycle, and we can choose several different kinds of cell cycle inside PhysiCell, but we still have always this notion of multiple phases, which are all linked together by fixed transition rates. And we have something similar for death models, so for apoptosis or necrosis, where this death can be triggered using a fixed rate for activating this apoptosis or necrosis. So this is already very useful, but still we have inside cells a lot of complexity and, more importantly, of regulation, which is hidden inside the intracellular level, at the level of signaling. For example, here we have some very simplistic version of the pathway, the signaling pathway regulating apoptosis or cell proliferation. Here we can see that the cells can receive multiple signals from the microenvironment, such as the presence of cytokines or chemokines or hormones, or the receiving signals such as survival factors, growth factors, death factors, can also receive some signals triggered by the presence of extracellular matrix around the cell. And so all of these signals from the microenvironment will then be used to activate some signaling cascades inside the cells. And all of this will then be used to regulate the apoptosis or the proliferation of the cells. And so we need something to be able to represent all of this complexity inside PhysiCell. And so what PhysiCell provides, fortunately, is our signals and behaviors. So signals can be seen as some inputs that the cell is receiving from the microenvironment, such as the presence of drugs around the cells of chemokines, cytokines, growth factors, presence of extracellular matrix around the cell. And PhysiCell also provides behaviors, which are actions that the cell can take, such as trigger apoptosis or trigger cell proliferation. So what we need to be able to represent intracellular signaling is something to glue together signals to behavior, to have behaviors which react in function of signals according to all the biological knowledge that we have of the signaling pathways which are orchestrating these two phenotypes, for example, which are apoptosis or proliferation. And so what we want is to have intracellular model that can be interfaced with PhysiCell to compute the behaviors from the signal. And with this, what we will be able to simulate are, for example, drug treatments. So we'll have some drug which will activate some signals, which will then modify something inside our signaling pathways, and will trigger some mechanism, some phenotype in our signaling pathway that then the behaviors of PhysiCell can trigger. With that, we also are able to represent mutants. So, for example, mutated proteins, which become either ineffective, deactivated, or automatically activated, for example. And Finally, we can also personalize these signaling models. So for example, we can take some data from the patient and personalize a generic signaling model so that we are able to have signaling simulation which are tailored for specific patients or cell lines. And so this effort will importantly simplify the description of multi-scale model, because we can already do it, but it involves a lot of code. And now what we want is to reuse existing intracellular model to be able to include them simply, efficiently inside PhysiCell. And one important aspect of this effort is that most of the modeling community is working already on intracellular model. And so we have many existing published models of signaling, which are, for example, in the case of Barrick et al., regulation of cell cycle, which is an ODE model, so very accurate but few variables. Or, for example, the model of prostate regulation by Montagu et al., which is not as accurate, it's Boolean, so it's just active or inactive states, but can include many nodes. And so we mainly have these two different formalisms to represent our signaling models, which are either quantitative or qualitative. So quantitative, an example of them would be ODE, the main example. So value can be any quantity. We can be, they are real numbers. And we have a notion of continuous time. So at any time, we can give the present concentration or quantity of a protein inside the cell, for example. The problem of this framework is that it's difficult to write, and formulas are complex, and we have a lot of parameters which are needed to characterize these descriptions. And it's also difficult to simulate large models, like above 100 components. It's very difficult to simulate ODEs of more than 100 variables. On the other side, we have qualitative frameworks. So, for example, Boolean framework, where values are only true or false, or absent or present, or active or inactive, for example. And we don't have a notion of time, but we have a notion of sequence of events. So here we only know that this happened and then that happened, but we don't know how much time elapsed between this and that. But to the contrary of ODEs, they are very easy to write. They are kind of close to natural language, actually. We can, for example, say that we need this protein and this protein, but not this other protein. And it's very easy to simulate large models, like hundreds or thousands. It's okay to simulate. So our goal here is to simplify the inclusion of existing signaling models, to allow multiple frameworks. Like we don't want to have only Booleans or only ODEs. We want to have everything possible. And we want this integration to be done with the signals of the end behaviors of PhysiCell. So the first example of this is PhysiBoSS, which was the inclusion of MABOS Boolean modeling inside PhysiCell. This was done by Gaël Letor in 2019. And basically what it does is that inside each of the cells of PhysiCell, we have one Boolean stochastic simulation, which will, for example, here in this example, simulate cell fate, so either survival or necrosis or apoptosis, according to the presence or absence of TNF tumor necrosis factor inside the microenvironment. And so according to the state of the microenvironment, cells will choose to survive or trigger apoptosis. And so how does it work is that periodically we will update our signaling model, signaling simulation. So every intracellularity, which is a value that we defined in our model definition, we will look at the state of the environment. We will then update the input nodes of our MABOS model. We will run our MABOS simulation, and then we will look at the phenotypes that the MABOSS model produced, the output of a simulation, and we translate these outputs to PhysiCell's behaviors. And so, for example, activating proliferation or apoptosis. And so one important aspect is that each cells run one single stochastic simulation using MABOSS, meaning that for the same state of the microenvironment, two cells can have different behaviors, different phenotypes. So you have some notion of heterogeneity inside your population. And so why use MABOSS? So MABOSS stands for Markovian Boolean Stochastic Simulator and was developed by Gauthier Stoll and Laurence Calzone here in Curie. And so as the name says, it's Boolean formalism and it's stochastic. But more importantly, it adds a new layer to classic Booleans, which is the notion of physical time. So it's called continuous time Boolean models, because we introduce basically a transition rate, which is some kind of kinetic rate, to say that this node will take some specific time to activate or inactivate. And we have to define this for each node inside our model. So with this notion of time in our Boolean simulation, we can couple our continuous time Boolean simulation to PhysiCell's time. And so, for example, what Gael did inside with the first version of PhysiBoSS is to simulate the effect of the TNF tumor necrosis factor treatment on a tumor. So without any TNF treatment, you can see that the size of the tumor is just increasing with time. But then when we start treating it with TNF, we see that at first we have an initial decrease in the size of the population, but then cells become resistant to TNF and the tumor starts growing again. So Gael also tried some different treatments. So for example, interrupting the TNF treatment after some time. But since the cells after some time are already resistant to TNF, you can interrupt the treatment, it won't have any effect because the cell will just keep growing. Resistant to something which is absent, won't change much. Gael also tried to increase the quantity of TNF inside the microenvironment, but since we are using Boolean formalism inside, we are just representing the presence or absence of TNF. We don't have a notion of dosage of TNF. So in this case, again, it won't have any effect to increase the size of the TNF treatment. What Gael also tried is this idea of creating pulsative treatment, so repeated treatment with interruptions. And here we can see that we can have some timing of a treatment which will make the tumor size go down because the cells basically won't have time to become resistant. What Gael also tried is to represent some heterogeneity inside the tumor. So here, for example, we have two different types of cancer cells inside our tumor. One, which is the classic one that she simulated before, and a new one, which is a double mutant, which is resistant to TNF. And so she was able to simulate the tumor with both populations, where you see the orange population, which is the one which is not naturally resistant to TNF, so which goes down at first and then become resistant. But the purple one is already resistant and just keeps growing despite the TNF treatment. Gael also tried the effect of to represent the necrosis, to have a necrotic core at the core of a tumor, and to show its effect on the size of the population. So now I'm going to present you PhysiBoSS 2, which is the new implementation of PhysiBoSS, which is now included inside modern PhysiCell. So first, a bit of history. So PhysiBoSS started as a fork of PhysiCell 1.1, which was May 2017, like already 6 years ago. And so starting from that point, both forks started to diverge. So PhysiBoSS started to develop and to add new functionality specific to this intracellular signaling inside of PhysiCell. But PhysiCell added more and more functionalities and became basically modern PhysiCell. And so, after some realization that it would be impossible to merge in this state PhysiBoSS inside recent PhysiCell, we started to have meetings together with Barcelona Supercomputing Center and Indiana University, people from PhysiCell, to merge back PhysiBoSS into PhysiCell, to try to develop a plan to achieve this. And so 2 years later, a little bit that 2 years later, PhysiBoSS 2 was finally merged back into PhysiCell 1.9 as an add-on. So what did we do in more details? So we tried to have some kind of modular architecture where we have on one side PhysiCell, like core PhysiCell, on the other side MABoSS, and we try to define some piece of code which basically binds the two together, so that PhysiCell will ask the add-on to update the cell. This add-on will ask MABoSS to run the simulation and then give back the update to PhysiCell. And so the idea is that with this architecture, we are able to update either PhysiCell or MABoSS without breaking anything, just with slight modification to the add-on subnet. And so we are actively developing and adding new functionality to PhysiBoSS, and PhysiBoSS 2.2.1 was released last week with PhysiCell 1.13. And so how does PhysiBoSS work more in the details? So we have to define, to describe our model inside the XML definition that is used by PhysiCell. And so the first thing we have to define are the model files that MABoSS will be using. So in the case of MABoSS, it's a BND for the network description and a CFG file for the simulation settings. Then we need to define the intracellularity, so the period of update of this intracellular model. Then we have some others, more complex parameters such as scaling or time stochasticity that I won't go into the details today, but in the next session. And then we can also modify initial values of your model and parameters, and also something new that we introduced recently, which is the mapping. So the idea of the mapping is that we want to automatically bind PhysiCell and MABoSS together just using the XML definition. So there are two components to this mapping. The first one are the input nodes. So how to link PhysiCell signals to MABoSS input nodes. So for example, say we want to have a mapping which says that the oxygen outside the cell will inhibit the node A inside our Boolean model. So we create this input category. We link together the signal called oxygen, which is called the PhysiCell name, and the intracellular name A, which is a Boolean node inside our model. We define that this action is an inhibition, and then we need to define a threshold above which the node A will be inactive because there is too much oxygen, and below which the node A will be active because there is not enough oxygen. So in this case, we choose 10. And we can also define another threshold so that it will be, we can represent hysteresis, but in this case, we are not using it. Then you also have the other part of the mapping, which are the outputs. So linking MABoSS output nodes to PhysiCell's behaviors. So for example, here, say we want our Boolean model node C to control apoptosis and to activate apoptosis when C is active. So we create this output and we link together the behavior apoptosis to the intracellular name C. We say that the action is an activation. And then we need to define two values. One, which will be the apoptosis rate when the node C is inactive. So this is the base value, which was 0. And one, when the node C is active, which will be the apoptosis rate again. So in this case, we choose 5. And we can also add some extra settings, which says that when C will become active, the apoptosis rate won't jump immediately from 0 to 5, but will actually increase gradually until reaching 5. And we can say that it will take 5 intracellular DT. And so PhysiBoSS 2.0 is also compatible with PhysiCell Studio. And so you're able, inside the graphical interface of PhysiCell, to completely define your XML settings files. So you're able to choose the BND and CFG files that you want, to configure your parameters, to add initial state, mutant parameters, and the mapping. And you are also able to visualize your simulation inside PhysiCell Studio. So we added a specific PhysiBoSS visualization, where you are able to color in green or red according to the activity of each node inside your Boolean model for every cell. And finally, I'm going to present you the intracellular interface, which is really the glue to link together PhysiCell and the intracellular models. So what we did is that we defined a pure abstract class, what is called a pure abstract class in C++. So it's just some kind of API which is not by default implemented. And so then different framework can define their own implementation of this interface. So first, for PhysiBoSS, we define MABOSS intracellular, which is really where PhysiBoSS add-on is defined. Then we have the Roadrunner intracellular, which is implementing simulation of ordinary differential equations and was developed by Furkan and Randy. And finally, we have DFBA intracellular, which represents metabolic pathways and so computes flux balance analysis inside each cell. So this was developed by Miguel Ponce de Leon. And of course, other intracellular frameworks are welcome and just need to implement this, to create a new implementation of this intracellular interface to add them. And so what they need to do more concretely, and this is the definition of this API, they need to define a new string for their intracellular type. They need to implement a new function which parse their own specific portions of the XML cell definition and to be able to fill their model description inside PhysiCell. Then we need to implement a function which defines what should they do when the cell starts, when the models are created. What function which says when is it time to update the model. So for example, just based on the intracellular DT like we did in PhysiBoSS. Then actually what should we do? What should the simulation do when they update the intracellular model? So in the case of MABOSS, which is adjusting the inputs of the MABOSS model, simulating, and then updating the behaviors then based on the outputs. And then other functions such as modifying the parameter values, displaying the states of the intracellular model, or cloning the intracellular, for example, when to transmit the intracellular from a daughter cell, mother cell to a daughter cell at division, or also when cells are dying, how to destroy this intracellular model. So all these new implementations need just to define these new functions in their own implementation of intracellular. And so as perspective, what we want to do now, that we already have something which works, but we want still to do more. So for PhysiBoSS, we want to add the support for more complex mapping rules. For now, we already have something which is good enough, but we want to have more complex things such as combination of signals or combination of nodes, and also notion of stochasticity. We also want to improve PhysiBoSS support inside the PhysiCell tools. So for example, support in PC data loader to import the intracellular simulation output, or in physical to be able to edit the XML definition, the intracellular part of the XML definition. And finally, we also want to develop tools and methods to create PhysiBoSS simulation directly from spatial omics data, such as spatial transcriptomics. And more generally, for the intracellular implementation, what we want to do next is to standardize the intracellular data output, and then also to add the possibility, the support for having multiple intracellular models inside each cell. For now, we can just have one unique type of intracellular model per cell, but we want cells to be able to have both Boolean and metabolic models, for example, inside. And so I will finish by thanking all the people which are involved in this effort. So all the people at Institut Curie who started by developing PhysiBoSS and developing PhysiBoSS, and who are still developing PhysiBoSS with me. And also people at Barcelona Supercomputing Center with who we are still actively collaborating into improving PhysiBoSS. And finally, also Randy and Paul from Indiana University, which helps us to reintegrate PhysiBoSS back into PhysiCell, and with which we are collaborating every day. And finally, Gael for starting all of this collaboration and starting PhysiBoSS. And so with this, I will thank our founding partners for PhysiCell and for PhysiBoSS. And I will see you in the next session, in session 9, where I will show you in more details how do we simulate TNF treatment inside PhysiBoSS 2. So we'll try to reproduce something similar to what Gael did in PhysiBoSS 1, but this time in PhysiBoSS 2 and using the graphical interface of PhysiCell. So thank you and see you in the next session.